Hi, we're Phoenix Aerospace, and this is our solar satellite UAV. So let's meet the team. I'm Ryan Bryce, I'm the team lead.
I'm Tyler Wilhite, I'm head of configuration.
I'm Jared Hinckley, I'm the capture manager.
I'm Haley Wilson, I'm head of CAD and graphics.
I'm Carson Campbell, I'm the head of the aero and control team.
I'm Anthony Pascal, I'm head of propulsion.
I'm Ben Miller, I'm head of weights and structures.
I'm Caleb Besmer, and I'm system avionics lead.
So overall, for mission requirements, the general concept is we need to be equal to or better than all the other aircraft that are available today. So let's go next. And then for the flight profile, we're going to be taking off and landing at 9,000 feet. Our cruise is going to be at 60,000 feet for year spans, and then we're going to land every year for maintenance. Next. Schedule, overall, this is what we use for our Gantt chart, and ultimately it's going to end with our design report being due at the end.
So for optimal endurance flight, we're going to be operating at a low power and thus a low speed and a low drag. So with this in mind, our goal for developing the wing plan form was to develop something that is capable of all these. So when looking at our airfoil, we wanted to focus on low drag, so a high L/D value. This led us to the Epler E216. Now for our aspect ratio for endurance flight, we want a higher value. And when looking at our benchmarked aircraft, we came to an estimated value of 18. Now to mimic an elliptical lift distribution, we came to the conclusion that a tapered and swept wing combination would be ideal, which leads to the benefits of the elliptical lift distribution without the downsides and less induced drag. So for our future plans, we plan on increasing the span and the chord. This is going to lead to an increase in our aspect ratio, a decrease in our wing loading, and a decrease in our cruise velocity.
Our goal is continuous flight for propulsion. We will complete this through solar panels, batteries, and electric motors. We use a decision matrix with 5 options, and through it we decided that our third with a double hex motor, Scion battery, and the 6-GM solar panel was the best option. Our future plans are to decide on the propeller due to the fact that we were using perfect propellers for our calculations to start, and to optimize the thrust to weight ratio.
Alright, so for weights and structures, our goal was to design a structure that was lightweight and strong enough to endure pretty much any conditions our aircraft could encounter. Our current material selection is carbon fiber for the ribs and spar because it's strong and light, and aluminum 2024 alloy for the skin. Materials that we're considering for future internal structure would be foam metal, where the base metal is aluminum or titanium, and carbon nanotube reinforced polymer. So possible ridge structures include this structure with triangular cutouts for the rib, and this structure with circular cutouts for the rib. Thank you.
The main goal for the avionics was to have consistent and continuous atmospheric observations at high altitudes. And we needed a sensor, an FMV camera, and a still high resolution camera as an optional, and along with the GPS autopilot. So the NASA approved TAMDAR sensor measures humidity, pressure, winds, temperatures, icing, and turbulence. It weighs very little and will send all of our data to the ground via satellite. We chose a gimbal camera because it can act as an FMV and still camera for the optional, and it is weather sealed, 360 degrees rotation, and has full HD photos and videos. The transponder autopilot we picked from Trig is ETSO certified. It functions up to 70,000 feet, and it weighs very little and have full flight system control from the ground. Thank you for listening, and go Pokes.